This is a short presentation describing the Yean teaching and research demonstrator constructed by NMIT. My name's Dr. Nikki Cooney. If you would like any further information on the many courses that we run at NMIT, please visit our website at www.nmit.edu.au. The Yean Teaching and Research Demonstrator is a collaboration between the Departments of Higher Ed and Vocational Education and Training, where a teaching and research demonstrator in agronomy has been set up at the Yean farm. This working farm is an establishment north of the Epping campus, just outside Melbourne. This collaboration is between both research and teaching staff, and also farm staff are participating in the successful delivery of this program. Our teaching staff at NMIT include Dr. Doug Rao, Nikki Cooney, Kathy Lawson, Rihanna Clayton, and we also have assistance from our farm supervisor, Patrick Eapy. We have some external collaborator from the University of Melbourne, DASA, who has extensive expertise in soil and agronomy modelling. We hope that as students you will learn a range of skills from the teaching outcomes of our Yean teaching and research demonstrator. These will include the demonstration of sustainable management practices in the field of agronomy. We are able to demonstrate how a collection of variety and cultivars responds to our soils, our climates, in the field environment. We are able to demonstrate practical skills such as chemical management, disease and pest management, fertigation practices. We will show you, with the aid of the research component of this demonstrator, how to conduct a fully replicated scientific trial, how to take plant growth analysis measurements, and understand the concepts underpinning these trials. And lastly, we hope to explore the concepts that you learn in the lectures, and you gain the skills to be able to apply these to the practical farming situations. So in this presentation, we are going to explore how science and agronomy can work together. I'm going to introduce some of the basics of the scientific principle. Why do we use scientific principles in agronomy? And I will finish by giving you details of how we have used these scientific principles in the Yean teaching and demonstrator. We will show you how it was set up and what research we hope to conduct on this site. So let us start from the basics, the concept of the scientific principles. The word science is a noun, and it has many meanings to many people, but in the context of this presentation and in the context of our teaching and research demonstrator, we shall think of science as the knowledge presented as facts or principles, as the knowledge gained by systematic study. This knowledge is based upon having, showing or involving a system, a method, a plan, a systematic course of reading, systematic efforts. In agronomy, the scientific method predominantly used is based on experiments to test a hypothesis. This experimentation may be conducted in a controlled environment, like say a glasshouse, or in paddocks and fields. An experiment will be set up, a theory will be tested by observations, and findings presented. So let us have a think about what we mean by theory. A farmer may have an idea about a management practice, or we may try to understand better how a crop responds to a particular climate or environment. So we construct a statement, and from this statement we form what we call as a hypothesis. When the scientific methodology uses a hypothesis, We call this the null hypothesis. It is usually shown by a capital H and a subscript 0. The role of the null hypothesis is to put the statement in a context that can be tested in the scientific methodology. A typical null hypothesis may state that there is no relationship between two measured phenomena. Or, another example of a null hypothesis is that a potential medical treatment has no effect. An example of a null hypothesis that may be used in agronomy might be the application of urea to wheat crops has no effect on yield. You will notice that all of these statements are negative. Once we have constructed our hypothesis, we will then test this hypothesis. This is called hypothesis testing. In order to test the hypothesis, we first collect data and measurements. In agronomy, the example of our nil hypothesis was that the application of urea to wheat plants had no effect on yield. We can collect data and measurements on wheat yield after we have applied urea. If we do this in a correct methodology, then we will be able to disprove our hypothesis. We are likely to establish a set of data. When we examine this data, we refer to statistical testing, which allows us to assign a certain amount of confidence in our results. We may be 99% confident, 95% confident, or 90% confident. These tests will be conducted in the discipline statistics. In modern day science, the central task is to give a precise sense if the claim or the hypothesis that you are making is capable of being proven false. This is why we aim to reject or disprove a null hypothesis. If you collect data in your controlled experiment and you showed a statistically significant change in yield after urea application, the null hypothesis is rejected. We may recommend using this product to industry if the null hypothesis is rejected. We do this because it gives us a precise sense in which a claim is capable of being proven false. Therefore, science proves statements are false. It does not prove statements are true. So what is the industry perspective on science? Well, I have compiled an example that may make this clear. The following is a conversation taking place between a crop grower and a consultant. The farmer asks the crop consultant, "I have seen an advert for a new fertilizer product. Should I apply this product to my paddock?" The advisor would want to know some more information. What do you want the product to do? The farmer states that he would like this product to increase his winter wheat yield while maintaining his high grain quality in rainfall seasons, as these are the times he's experienced difficulty with this relationship. The advisor may state to him, "I've seen some research done on this product and it was found to be effective in improving yield in tropical Queensland, but to the best of my knowledge it has not been tested in South Victoria, where the climate is temperate and the rainfall higher." The advisor states the only way to really know for sure is to conduct a controlled experiment on your farm. Therefore, in the example I have just stated, the only way to determine if this particular product is worth using is to test the product. If the farmer were to use the new product on a whole paddock, then he would not be sure whether the effect was due to the seasonal variation on yield or if it was due to the product. A controlled experiment is a great economic solution. It also allows you confidence in the observations that you are seeing. It is important when conducting such experiments that the farmer only changes one parameter at a time in his experiments. Therefore, one parameter is usually one treatment. If the farmer were to change more than one parameter, as an example, he might add a new fertilizer product and irrigate. He cannot be sure what combinations of events would have changed his yield at the end of the season. There are 4 possible outcomes. A change in yield may have resulted from none of the treatments. A change in yield was due only to the irrigation treatment. A change in yield was due only to the new product. Or a change in yield was due to the interaction of both the irrigation and the new product. A properly designed, well-replicated trial with appropriate controls allows you to get past these problems with not being sure which outcome is caused the desired effect. Sustainable farming is ideally a balance between producing the highest value products with the minimal amount of inputs. Inputs into cropping can be expensive. One of the climate components about Australia is that it is due to large seasonality. That means there are large changes in climate between each seasons. If you have an area with large seasonality and you conduct a new management practice, if you do not do this in a proper, replicated and well-designed trial, you can never be sure if the impact of your management practice is due to the seasons or due to the practice. Therefore, you need confidence in your management decisions to assist with cropping success. This is why the scientific method can be a very valuable tool. At the NMIT Yean Teaching and Research Demonstrator, we have selected 2 paddocks to demonstrate principles in agronomy. Paddock 7 demonstrates different crops' responses to our soils and climate. As well as the different crop responses, we have applied strips of urea so we can compare how different species will react on our soils and in our climate. We have a 3rd section on paddock 7, a strip across all of the varieties, which allow us to compare the application of urea and potassium to these crops. Again, we are able to compare them on the same soil type and in our climate. In paddock 5, we are implementing the scientific method. We have set up a controlled experiment in this paddock to test the response of urea. There are 2 experiments. The null hypothesis of these experiments are that the application of urea to wheat plants has no effect on crop growth, development and yield. The first experiment, testing our null hypothesis, is a replicated experiment where 3 treatments are compared. We will be able to compare a control against an area where urea has been added. The second area is a replicated experiment where we will investigate the response of the concentration of urea to crop growth, development and yield. This slide summarizes the layout of the experimentations and some of the thought and design that went into the experimentation at the Yean Teaching and Research Demonstrator. Our experimental plan is stated below. We compiled a plan, we conducted initial soil tests, we cultivated our soil to remove the pasture that was currently present, we sowed a wheat crop, we allowed the wheat crop to establish and grow, where to date, in June, it is about growing stage 28 to 30. We monitored and managed for pests, disease and weed infestation throughout the experiment. We identified plots and applied urea product. we collected data. We will conduct statistical analysis on the collected data, and we will either recommend or not recommend this product based on the rejection of our null hypothesis. The image on the slide is an image of Google Maps of Paddock 5 at the Yean farm. There are 8 pins shown. These are GPS coordinates of the soil samples collected. We collected these soil samples before the experiment was conducted and the soils were turned over. The table on the slide shows the results of our soil tests. We have the sites listed, the GPS coordinates, which are called eastings and northings, the structure, which was a description compiled by our scientists, a field texture description, and the results of the pH. We have some variation across the paddock in our soils, and we will select certain regions in this paddock to conduct our experimentations. Once all the data is collected, statistical analysis will be conducted. Averages for all treatment observations will be calculated. Standard deviations from treatment observations will be calculated. Statistical analysis will be conducted to determine if the treatments were significantly different. Students will discuss their findings and conclusions will be determined. This brings us to the end of describing our teaching and research demonstrator at Yean. I hope you enjoy learning about the scientific methods and the agronomical practices that we will be showing.